All right. So matrices will act on Euclidean space, right? So we have Cn, and you have some vector. If you have a vector in there, then the 2 norm of that vector is just the square root of the sum of the absolute value squareds. And if you have a matrix, A equals Aij, an n by n matrix, then it acts on the vector space Cn, and the norm of the matrix is the amount that it stretches. Okay, so A is the sup of norm Ax, the 2 norm of Ax, where x runs over the whole unit ball. So it's sort of the maximum stretch. The image of the open ball is always an ellipsoid. I'll show you why that's true in a second. Okay, so the norm is not so easy to compute by hand, but to get a handle on it, you need to know about the adjoint, right? So A star is the conjugate transpose, Aj conjugate, and it satisfies the property that if you have 2 vectors x and y, then Ax inner product y is the same as x inner product A star y. Okay. And the other place you see these adjoints is that a matrix is called normal if it commutes with its adjoint. Okay. So in particular, A star A is self-adjoint, because if you take this adjoint of that, adjoint reverses multiplication, and you get A star and then A star star, but A star star is A. Okay, so it's self-adjoint. So that means that it's diagonalizable with respect to an orthonormal basis. Okay. Say F1 up to Fn, so that A star A with respect to this new basis, let me call it F, is just lambda 1, lambda 2, lambda n. Now if you have a self-adjoint matrix, right, if you take this lambda 1 down to lambda n, apply it to a vector x1 to xn, and take the inner product with x1 to xn, then that's just equal to the inner product of lambda 1 x1, lambda 2 x2, lambda n xn, inner product with x1 to xn. Oops. And that's the sum of lambda I xi squared from I equals 1 to n. So in particular, you can see that this is always some convex combination of the eigenvalues. Okay, now when you take A star A, x inner product x, you can use this property of A star of A and A star to take the A star to the other side. It becomes A star star, which is A. Ax inner product Ax. But that's just the square of the norm of Ax. So that's greater than or equal to 0. So if you compare these two things, this is the convex hull of the lambda i's. So this tells you that the eigenvalues for A star A are all positive. Okay. Eigenvalues of A star A are non-negative, I guess is better. Okay. So that means that A star A has a positive square root. Okay. Positive square root, which I'm going to call absolute value of A, which has matrix square root of lambda 1, square root of lambda 2 down to square root of lambda n, diagonal, with respect to this same basis F here. Okay. Now this matrix has a nice property relative to the norm of A, because we have, from here we have norm of AX squared is AX and the product AX, which is A star A X and the product X. But absolute A squared is also equal to A star A. So this is absolute A squared X and the product X. And absolute A is self-adjoint. Okay, so this is equal to absolute AX, which is the norm of absolute AX squared. Okay, so A and absolute A have this property that they take the same norm on all vectors. So I can define another linear transformation U, so that U of absolute AX is equal to AX. This is defined on the range of absolute A. And we can define UX equal to 0 if X is perpendicular to the range of absolute A, and this is the same as saying if X is in the kernel of absolute A, which is the kernel of A. Right? They have the same kernel because of this formula, but since A is self-adjoint, the kernel is orthogonal to its range. Okay? So U is what's called a partial isometry. Because on the range of X, it preserves the norm. So it's isometric there, but on the orthogonal complement, it's 0. And it's designed so that A is equal to U times absolute A. And that's called the polar decomposition. It's just like the polar decomposition of a complex number. Complex number, you can write it as e to the I theta times r, where r is the absolute value of your complex number. This is the absolute value of your matrix. And this is a rotation, just like e to the I theta is. Okay. All right. I want to say a bit about order on matrices. So if A is self-adjoint, then it's diagonalizable. And we say that A is positive if the lambda i's are all positive, for all I. Okay? And I say that A is less than or equal to B, which is also, has to also be self-adjoint, if b minus a is positive. Okay. All right. And so I want to use this order to do a couple things. One I want to note is that if a is less than b and x is a matrix, then x star a x is less than or equal to x star bx. Why is that? That's because when we subtract them, you take, you have x star b minus a x, x inner product x, all right? So let me just say here, this is true because of this inequality over here, if and only if axx is greater or equal to 0 for all x. Okay? And this somehow is a basis independent thing. We don't actually have to compute the eigenvalues to check that. So that's the advantage there. So let me do that here. Look at x star b minus a x. Well, that's equal to b minus a acting on big X, little x. And I take x star to the other side, it becomes x star star, which is x. So this is a vector y, and this is the same vector y. B minus a is positive, so that's positive. Okay. And there's one more thing about the order I want to mention, because we want to come back and get a handle on the norm of a. So we have norm of a is less than or equal to 1 if and only if the norm of absolute a is less than or equal to 1. And that's true if and only because, right, and this has the eigenvalues square root of lambda 1 to lambda n. So this is the max of square root of lambda I, where lambda I are eigenvalues of a star a. Well, norm of a is actually, so this is a formula. All right. So you can compute that, not so easily by hand, but you can compute that on a computer, because you can, if you have A as a matrix, you can compute A star, so you can compute A star A. That's easy. Now you're looking for the largest eigenvalue of that matrix, and there are algorithms for finding the largest eigenvalue of a matrix. Okay, so it can be computed. Of course, the bigger the matrix, the harder it is. But if you're only, you don't have to compute all the eigenvalues. You only have to find the largest one. Okay. So this is true, and this is true if and only if norm of a star a is less than or equal to 1, because the eigenvalues square root of lambda I are less than 1 if and only if the lambda i's are less than 1. But this is true if and only if a star a is less than or equal to the identity. Because when a star a looks like this, when you compute the identity minus a star a, that's 1 minus lambda 1 down to 1 minus lambda n. And that'll be positive if and only if all of the lambda i's are less than 1, less than or equal to 1. Okay. So I get this inequality, and that's going to be useful. Okay. So, von Neumann's inequality. So here's the question. If a is norm less than or equal to 1, and p is a polynomial, what can we say about the norm of P of A? So why was von Neumann interested? Well, von Neumann was very interested in quantum mechanics, and he was very interested in using bounded operators on Hilbert space, which is the infinite dimensional analog of C to the n, for representing quantum mechanical systems. Okay, and in particular, he felt that you should be able to think of operators or matrices as quantum variables, and you should be able to plug them into polynomials and get reasonable estimates. Okay. So so let me just say a little bit about the easy case. If A is normal, then it's diagonalizable with an orthonormal basis, right? All right, and these lambda i's are eigenvalues. So you certainly have if A fi is equal to lambda I fi, then you have A fi inner product fi is equal to lambda I fi inner product fi is equal to lambda I. And that tells you that lambda I can't be too big. Lambda I is less than or equal to, by Cauchy-Schwarz, the norm of AFI times the norm of FI, which is less than the norm of A times 1 times 1. That's less than or equal to 1. So the lambda i's belong to the closed disk, the set of all complex numbers Z, such that Z is less than or equal to 1. Okay, and if I take P of A, it's unitarily equivalent to taking the polynomial here, but when you have a diagonal operator and you take powers of it, you just get the powers of the diagonal entries. So this is P of lambda 1, P of lambda 2, down to P of lambda n. And you see that the norm of P of A is then just the max of P of lambda I, where lambda I are eigenvalues of A. And so that's less than or equal to what I'm going to call the infinity norm of P, which is the sup of P of Z, where Z runs over the whole disk. Okay. However, if A is not normal, it's not clear what's going to happen. Say A is this matrix. So that's a Jordan block. It isn't too hard to figure out what the powers are. I mean, the A squared has 2 1s here, A cubed has a 1 there, and A to the n is 0 for n bigger or equal to 4. So if P of Z is equal to C0 plus C1Z plus C2Z squared plus higher order terms, then P of A looks like C0 down the diagonal, C1 here, C2, C2, C3. It's a nice formula, but now it's not so easy to compute the norm. So it's not clear what we should expect in von Neumann's question there. So, the theorem known as von Neumann's inequality is that if A is less than or equal to 1 and P is a polynomial, then the norm of P of A is less than this P infinity, the soup over the disk. Right? It's easily true if it's normal, but it's not at all clear for these others. Now, von Neumann gave a proof of this, an interesting proof, and I'm going to tell you a bit about his proof. But then, some years later, there was a new proof which uses, even in the case of matrices, it uses infinite dimensional ideas. Okay, so the first thing is, what is the closure, or the completion of the polynomials in this norm, right? The soup norm over the disk. If you take a limit of polynomials, they're all continuous functions on the closed disk, so a uniform limit of continuous functions is continuous. Any limit will be continuous on the closed disk. But polynomials are also analytic. Okay, they have a power series expansion, a rather nicely converging power series since it's finite. So in particular, these functions are analytic on the open disk. And if you take a uniform limit of analytic functions, you get analytic functions. So the completion is what's called the disk algebra. This is the set of all functions f, which are continuous on the closed disk, such that f restricted to the open disk is analytic. Okay. So it's a very important algebra, but inside this algebra we have lots of functions that aren't polynomials. In particular, we have rational functions, and I want to pick out the Mobius maps. So if I take a point A in the disk, then let WA of Z be Z minus A over 1 minus A bar Z. So if you've taken complex analysis class, you know that this is an analytic function that maps the extended complex plane one-to-one onto itself, the Riemann sphere. And it's easy to see that this takes the circle to the circle. So if I take e to the I theta minus A over 1 minus A e to the I theta, A bar, then that's equal to e to the I theta minus A over e to the minus I theta minus A bar. That's a complex number over its complex conjugate. So this has modulus 1. So it takes the circle to the circle, takes the unit circle to this unit circle, and it takes the unit disk to the unit disk, and it takes the outside of the disk to the union infinity to outside of the disk union infinity. So this isn't a polynomial, but it's a limit of polynomials. And so this inequality should extend to uniform limits of polynomials over the disk. Okay, so if this inequality is true, it should be true for that function. So I'm going to take it a to norm less than or equal to 1 and look at WA of A. So what is that? I mean, Z, you just, wherever you see a Z, you put in an A. So this is A minus A times the identity. And we're dividing by identity minus A bar A. Okay, so you get 1 minus A bar A inverse. And this makes sense because the eigenvalues of A have to all lie in the disk. So therefore, the eigenvalues for A bar A lie in a disk of radius A, strictly smaller. So 1 is not an eigenvalue, so that is invertible. Okay, so WA of A is less than or equal to 1 if and only if, all right, I can use this property that if and only if W of A star W of A is less than the identity. Okay. So we just multiply this out. So this is if and only if I minus A bar A star inverse A star minus A bar identity times A minus A identity times I minus A bar A inverse is less than or equal to the identity. Okay, but I can multiply on the left and the right by 1 minus A bar A star and 1 minus A bar, and since this is less than or equal to 1, this will give me a new inequality, and it's equivalent because I can go back because it's invertible. So this is if and only if A star minus A bar I, A minus AI, is less than or equal to I minus A bar A star, I minus A bar A. Okay, so let's just multiply that out. That's A star A minus A star minus A bar A plus absolute A squared identity. And this is equal to identity minus A bar A star. Ha! When I take the adjoint of that, the A bar becomes an A. So this becomes A, right? Y minus, did I do it right? A, yeah. 1 minus A star, right? So, oh no, I'm right. Okay. Did I do something, did I do it right on this side? No. So, that's not there. Okay, sorry. So, it's 1 minus A star minus A bar A plus absolute A squared A star A. Okay. So a bunch of stuff cancels. This A bar A star cancels that. This minus AA cancels. Oh. I have to do the calculation right though, and then it cancels. All right. Sorry. Okay. And so this is true if and only if, let's bring all the A star A's to the left, 1 minus A squared A star A is less than or equal to 1 minus A squared times the identity, and we can cancel those off. And so that's if and only if A is less than or equal to 1. So, in particular, if A is less than or equal to 1, this is true for that particular function. But now we can multiply a bunch of them together. E to the I theta times this product, I equals 1 to m, say, of z minus ai over 1 minus a bar z. This is called a finite Blaschke product. It takes the circle to the circle, because when you multiply a bunch of numbers in the circle, it stays in the circle. So b of the circle is contained in the circle, and b of the disk is contained in the disk. So therefore, infinity norm of b, the sup over the disk, is always 1. And if I take b of a, what I get is e to the I theta times WA1 of A, WA2 of A, WAM of A. It's a product of a bunch of operators who all have norm 1, so this is less than or equal to 1. And then he argued that, well, every polynomial of norm 1 is in the convex hull of these b's. And then that's how you do it, right? So the convex hull of the set of all finite Blaschke products closed up in the infinity norm is the unit ball of the disk algebra. Okay. And that's how he proved the theorem. But what requires proving this result, which is not so easy either. So I'm going to tell you a different proof. So it's the Sz.Nagy, Sz, short form for what the word that means saint in Hungarian, and for some reason it's silent. Everybody says Sz.Nagy, okay? Sz.Nagy dilation theorem. So we start with our A less than or equal to 1. I want an operator D, or matrix D, so that the matrix AD is isometric. In other words, it preserves norm. So A either leaves the norm the same or reduces it. I want to fill in the gap with D. So what do I need? I need that the norm of x squared should equal the norm of ax dx squared, which is ax plus dx dx, which is A star A plus D star D. I'm going to make D positive so I don't have to worry about taking adjoints there. So here I get this. So if this is true for all x, this means that A star A plus D squared is equal to the identity, and therefore D squared is equal to identity minus A star A, which is positive because A star A is a contraction. So it has a positive square root, right? So dA be the positive square root and then it has this property. Okay? And then I'm going to write down the following matrix: A, dA, dA star, which is different because that's the identity minus AA star to 1/2, minus A star. I claim that is a unitary matrix. U star is equal to A star. dA star goes down here, and dA goes up here, and here I have minus A. So if I multiply them, you get AA star plus dA star squared there, and down here we get A star A plus dA squared. So those are both the identity. And then in the off-diagonal corners, here I get A dA minus dA star A. And here I get the adjoint of that. Here I get dA star minus A star dA star. I claim that 0. Well, you notice that A times A star A is equal to AA star times A. And then the same is true if I put a power there. For any k bigger or equal to 0, that's true. So therefore A polynomial in A star A is equal to the same polynomial in AA star times A. So let's take a sequence pk, and I want pk of x to converge to square root of x uniformly on 0, 1. We know we can always do that, okay, by the Weierstrass theorem. And when I take such a limit, the left-hand side converges to A dA, and the right-hand side converges to dA star A. So this is 0. And this is also 0 because it's the adjoint of that. So this is the identity. So therefore U is unitary. It's not quite the unitary I want. Okay. What I want is a unitary W, which looks like this. The asterisks can be anything we want as long as I get a unitary. But this is block lower triangular. In finite dimensions, if you take a block lower triangular matrix and it's normal, that is block diagonal already. But I can do this in infinite dimensions. So I'm going to form a Hilbert space, and it's going to be a direct sum of copies of my space Cn from minus infinity to infinity. So it's so let me give them names. Let me call them let me call these hk, k equals minus infinity to plus infinity. So here I say I have h minus 2 direct sum h minus 1 direct sum h0, which is my original space. Like that. And so h0 is going to correspond to this middle bit. So this I'm going to call this k minus my original h0, and then this is k plus. So all of this stuff is k minus, and all of this stuff is k plus. And then I'm going to build my matrix like this. First, I'm going to put this unitary that I constructed over there. We'll have to flip it around. So dA star dA minus A. So that's a little unitary. And what it's doing is that this u here, u is mapping h minus 1 direct sum h0 onto h0 direct sum h1. Okay, the way I've written it. Okay? But to make it a unitary, it has to be an isometry, and h1 is already used up. Where am I going to send h1? Well, I send h1 onto h2, and h2 onto h3, etc. Okay, so I put an identity there, and I need to map something onto h1 because h1's been mapped into h0. So I map h minus 2 onto h minus 1, and h minus 3 onto h minus 2, etc. And when you do that, you end up with an operator which is an isometry mapping the whole space onto the whole space. That's a unitary. But I needed infinite dimensions to do this. Okay, and the nice thing is that if A acts on an infinite dimensional space, this same argument works. Okay. All right, so let's come back to the inequality. Well, when I take polynomials in this, let me call this W. Okay, look at it. So when you take powers of W, it keeps its lower triangular form. And you get a to the k here. So when I add up linear combinations of that, I get any polynomial. And it looks like a big operator that has P of A there. So it's easy to see that the norm of P of A is smaller than or equal to the norm of P of W. But P of W is normal. Even though this is infinite dimensional, the same norm estimates apply as worked in for matrices. This is the sup of P of lambda, where lambda is in the spectrum of W. Okay, you can't say eigenvalues anymore, but it's the same thing. So this is less than or equal to the sup over lambda in 1, because every unitary matrix has its spectrum in the unit circle. So this is P of lambda in the unit circle, and that's the same as P infinity by the maximum modulus principle. Okay, every analytic function takes its sup on the boundary. So in particular, polynomials take their sup on the boundary. So there's a simpler proof of von Neumann's inequality, and it implies something more, which turns out to be important, which is that if I take suppose I take some m by m matrix with coefficients in the polynomials, okay, then I can put a sup norm on it. The norm of this matrix Pij is the sup over z less than or equal to 1, we call infinity, of the norm of the matrix Pij of z. So you just plug in z over the unit disk, plug them in there, you get an m by m matrix, and you take its norm. And a similar sort of argument shows that if I take the norm of Pij of w, this is less than the norm of Pij. And so I get as a corollary, if A is less than or equal to 1, then when I take the norm of a matrix polynomials in A, that this is less than the sup norm of this over the unit disk. Okay. But it turns out that the converse is true, okay? So that when this inequality is always true, then it's norm 1. Of course, it's kind of, it's not so, I guess that's not so exciting here, but this notion of matrices is very important when you're going to more complicated situations. Other algebras other than the disk algebra, situations even where the algebras are not commutative. Turns out that these matrix inequalities turn out to be equivalent to a dilation. Something like this is called a dilation. And then there's a whole theory that says that in any reasonable context, a dilation occurs if and only if the appropriate set of matrix norm inequalities holds. And I'm going to stop there.
Does anybody have any questions?
Yeah.
Yes.
So when you take the direct sum of all those CNs, are you requiring some kind of convergence of things? Or?
Yes. So this is a Hilbert space. So when I have a vector v, which is a direct sum of vk, then the norm of v that has a 2 norm is the sum of the norms of the vk 2 norms squared from minus infinity to infinity to the 1/2 power. And that's a Euclidean space just like in finite dimensions. It's called the Hilbert space.
Okay.
Yeah.